Hello, and welcome to Sleep Science Space. Tonight, we're going to slowly drift into the unknown, into questions that science has not yet been able to answer. Even after centuries of discovery, the universe is still filled with puzzles, paradoxes, and quiet mysteries that remain unsolved. Some of these mysteries are vast and cosmic, stretching across galaxies, black holes, and the structure of space itself. Others exist much closer to us, within Earth's oceans, its atmosphere, and even inside our own bodies. These unanswered questions remind us that science is not a collection of final truths. Instead, it is an ongoing process, a story that continues to unfold with each new observation and idea. Every mystery represents an opening, an invitation to wonder, and a reminder that we are explorers living inside a universe far larger and more complex than we currently understand. Some physicists propose that the universe itself may have emerged in a similar way, that absolute nothingness is unstable, and that something is almost inevitable. Other theories suggest that our universe may be just one of many part of a vast multiverse in which countless universes form, each with its own physical laws. But this idea only shifts the mystery rather than solving it. If a multiverse exists, why does it exist at all? Philosophers sometimes argue that existence is the natural state of reality, and that true non existence may be impossible. According to this view, reality in some form must always exist. However, these ideas cannot be tested. No experiment telescope or particle collider can explain why there is being rather than nothing. Every scientific question ultimately rests on this mystery. Every star in the sky, every atom in your body, and every law of nature depends on a foundation we cannot explain. The simple fact that reality exists at all remains one of the deepest mysteries we face. Closely connected to this question is another unresolved problem: the origin of the universe itself. We can trace the universe's history back nearly 14 billion years to a time when it was extremely hot and dense. This event is known as the Big Bang. Yet what caused the Big Bang remains unknown. Scientists have reconstructed a detailed timeline of the universe, starting fractions of a second after its birth. During those earliest moments, space itself may have expanded at an extraordinary rate in a process called inflation. However, what triggered inflation, why it began, and why it eventually ended are questions that remain unanswered. Some theories describe the Big Bang as a quantum event, a tiny fluctuation in the fabric of reality that gave rise to space and time themselves. Other models suggest that the Big Bang was not the beginning of everything, but part of a repeating cycle, with universes expanding, collapsing, and being reborn over and over again. The mystery becomes even more complex when we consider the nature of time. If time itself began with the universe, then asking what came before the Big Bang may not even be a meaningful question. Our instruments, including the Hubble Space Telescope, the Planck satellite, and the powerful James Webb Space Telescope, allow us to observe the early universe in remarkable detail. We can measure its age, track its expansion, and study the faint afterglow left behind by its birth. yet the very first instant remains beyond our reach. We know the universe began, but the spark that set everything in motion is still hidden from us. Yet the spark that truly set the cosmos into motion, the original cause behind everything, remains hidden from us. We know the universe began, but the reason it began and what initiated that beginning is still lost in darkness. In the same way, time itself presents a mystery we experience constantly but cannot fully explain. Time always moves forward. The present becomes the past, and the future remains unreachable. We remember what has already happened, but never what is yet to come. A shattered glass does not reassemble itself. Heat flows from a warm cup of coffee into the surrounding air, never the other way around. In our everyday experience, time moves in only one direction. This one-way flow is known as the arrow of time. What makes it so puzzling is that the fundamental laws of physics do not demand it. At the smallest scales of reality, the equations that govern particles work just as well forward in time as they do backward. They are symmetrical. Nothing within them insists that time must advance in a single direction. And yet, everything we experience from memory to cause and effect depends on this irreversible flow. Scientists often link the arrow of time to entropy, the tendency for disorder to increase. The universe appears to have begun in an extraordinarily ordered state and has been gradually becoming more disordered ever since. But this only shifts the mystery. Why did the universe start out so ordered in the first place? Why was the initial entropy so low that time could even have a direction at all? Some physicists suggest that the arrow of time emerges from how information spreads and becomes inaccessible. Others argue that it is connected to the expansion of the universe itself. Still, none of these explanations fully resolve the problem. We live inside time every second of our lives, yet the reason it flows forward and only forward remains one of the most haunting unanswered questions in science. Much of the universe is also composed of something we cannot see. When astronomers observe how galaxies rotate, they encounter a troubling discrepancy. Stars at the outer edges of galaxies move far faster than gravity from visible matter alone should allow. By all known laws, those stars should escape into space. Instead, they remain tightly bound. The conclusion is unavoidable. There must be far more mass present than we can detect with our instruments. This unseen substance is known as dark matter. Dark matter does not emit light, absorb light, or reflect it. Telescopes cannot observe it directly, yet its presence is undeniable because of its gravitational influence. It holds galaxies together, bends the paths of light, traveling from distant objects, and leaves subtle imprints in the large-scale structure of the universe. Despite this, its true nature remains unknown. Scientists have spent decades searching for answers. Some propose that dark matter consists of undiscovered particles, such as weakly interacting massive particles. Others suggest actions, extremely light particles that rarely interact with ordinary matter. There are even theories proposing that dark matter could be made of ancient black holes formed shortly after the Big Bang. So far, none of these ideas has been confirmed. Sensitive detectors buried deep underground wait patiently for a single dark matter particle to collide with an atom. To this day, no definitive signal has been found. For now, this invisible mass, which outweighs ordinary matter by a factor of 5, remains one of the universe's greatest unsolved mysteries. Alongside dark matter, an even stranger force appears to dominate the cosmos. Space itself is not merely expanding, it is doing so at an accelerating rate. In the late 20th century, astronomers studying distant supernovae expected to find the universe's expansion slowing under the pull of gravity. Instead, their observations revealed the opposite. Galaxies are moving away from one another faster and faster over time. This acceleration implies the presence of an unknown form of energy embedded within space itself. We call it dark energy, though this name simply reflects our lack of understanding. Dark energy makes up nearly 70% of the total content of the universe, yet its nature remains completely mysterious. One possibility is that it is a property of empty space, a constant energy inherent to the vacuum. Another idea suggests it could be a dynamic field that changes over time. Some theories even propose that dark energy signals a deeper problem with our understanding of gravity itself. What makes this mystery especially unsettling is its impact on the fate of the universe. If dark energy remains constant, galaxies will drift farther and farther apart, leaving behind a cold, empty cosmos. If it grows stronger, it could eventually overwhelm all other forces, tearing apart galaxies, stars, and even atoms. We can measure its effects, but its true essence remains hidden. Dark energy acts as an unseen hand, shaping the ultimate future of everything that exists. At the same time, the laws of physics themselves appear delicately balanced in ways we do not fully understand. The universe seems finely tuned. If gravity were slightly stronger, stars would collapse too quickly to support life. If it were slightly weaker, galaxies might never form. If the electromagnetic force were altered by even a small amount, atoms would fail to bind together. The smallest changes in the fundamental constants of nature could eliminate the possibility of life altogether. This question is often described as the fine-tuning problem. It asks why the fundamental laws of nature have exactly the values we observe. There is no obvious reason for gravity, electromagnetism, or the nuclear forces to possess the precise strengths they do. And yet, if any of these forces were altered even slightly, the universe would likely be sterile, unable to support stars, chemistry, or life of any kind. Some scientists argue that this balance is nothing more than chance. Others suggest that reality may contain an enormous number of universes, each governed by different physical laws, and that we simply happen to exist in one of the rare regions where conditions allow life to emerge, a kind of cosmic lottery. Another possibility is that the apparent fine-tuning is not accidental at all. There may be a deeper principle, still unknown, that requires the laws of physics to take these exact forms. At present, we have no way to determine which explanation, if any, is correct. Still, when we look at the stars, the planets, and our own ability to ask these questions, it is difficult to ignore the feeling that the universe is remarkably suited for life. Why this is the case remains one of the most profound unsolved problems in science. Equally uncertain is the ultimate size of the universe itself. We do not know whether the cosmos extends forever or ends somewhere beyond our reach. The observable universe spans roughly 90 billion light years, but this limit is not a true edge. It exists because light has had only a finite amount of time to travel since the Big Bang. Beyond this cosmic horizon lies a region we cannot see and may never observe directly. One possibility is that the universe is infinite, stretching endlessly in every direction without boundary. If this is true, then space may contain an unlimited number of galaxies and stars, and perhaps countless worlds similar to our own. Another possibility is that the universe is finite but unbounded, similar to the surface of a sphere. In such a cosmos, traveling far enough in one direction could eventually bring you back to where you began without ever encountering an edge. Scientists search for clues in the cosmic microwave background, the faint radiation left over from the early universe. Subtle patterns in this afterglow may reveal information about the overall geometry of space. So far, observations suggest that the universe is very close to flat. However, this alone does not determine whether it is infinite or finite. For now, the true shape and extent of the cosmos remain unknown, hidden just beyond the limits of observation. When we observe distant space, we are also looking back in time. The most remote galaxies we can detect are sending us light that began its journey more than 13 billion years ago. Beyond them lies the unobservable universe, a vast region forever hidden from our view. This boundary is not a physical barrier, but a consequence of the universe's age and the finite speed of light. Reality continues beyond it, but we cannot know exactly what it contains. It may resemble what we already see, with galaxies and stars extending far beyond our sight. Or it may be fundamentally different, with regions shaped by conditions unlike those in our observable universe. Some models of cosmic inflation suggest that our visible universe is just one bubble within a much larger and more complex reality. If this is true, then most of the universe lies permanently beyond our ability to measure or explore. In this view, we exist on a kind of cosmic island. The sky above us represents only a tiny fraction of what may exist. The rest of the universe remains silent and unreachable, a vast unknown. Some scientists believe that other universes may exist beyond our own, but there is currently no way to prove it. The idea of a multiverse remains one of the boldest and most speculative concepts in modern science. This line of thinking suggests that our universe may not be unique, but instead one example among countless others. In this broader picture, each universe could operate under different physical laws, follow different histories, and even contain different numbers of dimensions. The idea does not come from imagination alone. Certain scientific theories naturally lead to it. Cosmic inflation, for example, may produce separate bubble universes, each forming with its own conditions as space rapidly expands. String theory also points toward a vast landscape of possible realities, each defined by different underlying parameters. If these ideas are correct, then our universe is simply one outcome among many. This perspective could even explain the fine tuning problem. We observe a universe suited for life because only in such universes could observers ever arise. However, this explanation comes with a serious challenge. If other universes exist beyond our cosmic horizon, we may never be able to detect them. No signal or light could ever cross that boundary. This places the multiverse in a difficult position, both fascinating and controversial. It stretches the traditional definition of science, because an idea that cannot be tested may remain forever speculative. Even so, the possibility that reality extends far beyond our observable universe, perhaps infinitely beyond it, remains one of the most intriguing ideas in modern physics. It hints that space and time themselves may emerge from deeper rules we have yet to uncover. Einstein's theory of general relativity already showed us that space and time are not rigid backgrounds. They are dynamic and flexible, capable of bending and stretching under the influence of mass and energy guiding the motion of planets and the paths of light. But this raises a deeper question. At the most fundamental level, what is the fabric of space-time actually made of? At extremely small scales, general relativity and quantum mechanics appear to contradict one another. Relativity treats space and time as smooth and continuous, while quantum theory suggests that reality should be granular, fluctuating, and uncertain. Reconciling these two descriptions remains one of the greatest challenges in science. Some ideas propose that space and time are not fundamental at all. Instead, they may emerge from something deeper, such as networks of quantum information or patterns of entanglement that collectively give rise to geometry. In this view, space-time is more like a surface with a deeper hidden structure beneath it that we cannot yet observe. Other researchers go even further, questioning whether time itself is truly real. It may be an illusion created by more fundamental processes operating beneath our perception. If this is true, then one of our most basic intuitions about reality would be wrong. Space and time feel like the stage on which the universe unfolds, yet the stage itself may not be what it seems. What space and time truly are remains one of the most profound unanswered questions in science. Quantum mechanics introduces mysteries that are just as unsettling. According to the theory, a single particle can exist in multiple places at the same time. Particles do not have definite positions until they are measured. Instead, they exist in a superposition, a spread of possibilities where many outcomes coexist simultaneously. An electron, for example, can pass through two slits at once, interfering with itself like a wave. Only when a measurement is made does the particle appear to settle into a single location. This behavior is not just theoretical. Experiments have repeatedly confirmed superposition not only for electrons, but for molecules thousands of times larger. Physicists have even created delicate quantum states in which objects exist in overlapping possibilities at the same time. Yet, despite decades of study, no one fully understands what this means. Does a particle physically exist in multiple places at once? Or does superposition simply reflect a limitation in our knowledge? Different interpretations offer different answers. Some suggest that reality splits into multiple outcomes, with each possibility unfolding in its own branch. Others argue that reality itself remains undefined until it is observed. Whatever the correct explanation may be, the fact that a single particle can appear to be in two places at once remains one of the strangest and most disturbing mysteries in modern science. Entanglement deepens the mystery even further. When particles become entangled, their properties become linked in a way that seems to ignore distance entirely. Changes to one particle are reflected in the other even if they are separated by vast distances, potentially across light years of space. This connection defies our everyday understanding of cause and effect and continues to challenge our deepest assumptions about how reality works. When one of two entangled particles is measured, the state of the other becomes known instantly, no matter how great the distance between them. This deeply unsettled Einstein, who famously described it as spooky action at a distance because it appeared to violate one of the most basic rules of physics. According to relativity, nothing should travel faster than light. And yet, repeated experiments have shown that entanglement is real. Photons, electrons, and even small collections of atoms have been entangled and then separated by kilometers while their correlations remain perfectly synchronized. No signal seems to pass between the particles. Nothing travels through space to carry information from one to the other. And yet their outcomes remain linked, as if nature itself keeps a hidden record, ensuring that both sides agree. What this truly means is still unclear. Some physicists believe this points to a fundamentally non local universe, one in which reality is connected more deeply than space and time alone can describe. Others suspect that entanglement hints at hidden variables, aspects of reality we have not yet discovered. Still others propose that information itself may be the most basic ingredient of the universe. Today, we already use entanglement in emerging technologies such as quantum computing and ultra secure communication. It works reliably in the laboratory, even though we do not fully understand why it works at all. The universe appears to communicate across distance in a way that defies ordinary explanation, and the mechanism behind it remains unknown. Equally mysterious is the role of observation itself. One of the strangest discoveries in modern physics is that simply measuring a system can change its behavior. In the famous double slit experiment, particles behave like waves when no measurement is made, creating intricate interference patterns. But the moment we observe which path a particle takes, that wave like behavior disappears. The result changes purely because the system was observed. Why this happens is still debated. One explanation is that the wave function, the mathematical description of all possible outcomes, collapses into a single result when a measurement occurs. But this raises a deeper question. What exactly qualifies as an observer? Is it a measuring device, a human consciousness, or does the collapse itself merely reflect deeper physical processes we do not yet understand? Some interpretations suggest that every possible outcome actually occurs, each one unfolding in its own branch of reality. Others argue that particles only appear to have definite properties once information about them becomes irreversible. So far, none of these interpretations has been proven correct. What is clear is that the boundary between observer and observed is far more subtle than we once believed. The universe seems to respond to being measured, and no one yet knows why. Gravity presents another enduring mystery. It is the force that dominates the large scale structure of the universe. Gravity binds planets to their stars, shapes galaxies, and governs the motion of entire clusters of matter. And yet, when compared to the other fundamental forces, gravity is astonishingly weak. A small magnet can overcome the gravitational pull of the entire Earth with ease. This imbalance has puzzled physicists for decades. The electromagnetic force, along with the strong and weak nuclear forces, operates with tremendous strength at tiny scales. Gravity, by contrast, appears almost negligible. One idea is that gravity spreads into extra dimensions beyond the three dimensions of space we can observe, diluting its apparent strength. Another possibility is that gravity is inherently strong, but its true nature is hidden by unknown physics at very small distances. Despite centuries of observation and theory, no definitive explanation has emerged. We still do not know why gravity is so much weaker than the other forces. This is not a minor detail. The delicate imbalance between forces is essential to the structure of the universe as we know it. Without it, stars, galaxies, and even the possibility of life might never have formed. Without this delicate weakness of gravity, stars and galaxies could never have formed. The very structure of the cosmos depends on gravity being just strong enough to shape matter, yet weak enough to allow complexity to arise. In this way, gravity's faintness is not a flaw, but a quiet mystery that makes the universe possible. At the deepest level, however, gravity exposes a profound problem in modern physics. Einstein's description of the universe and the quantum description of reality both work extraordinarily well, yet they refuse to fit together. General relativity explains the large scale behavior of space time and gravity with remarkable precision. Quantum mechanics, on the other hand, describes the microscopic world with astonishing accuracy. Each theory has survived every experimental test we have devised, and yet, when they are brought together, they clash. In extreme environments where both gravity and quantum effects should matter, such as inside black holes or during the first moments after the universe began, the equations collapse into nonsense. Infinities appear where meaningful answers should be. Mathematically, the two frameworks are incompatible. For decades, physicists have searched for a single theory that could unite them into a coherent whole. Ideas such as string theory and loop quantum gravity have offered intriguing possibilities, but none have yet been confirmed by experiment. Without a unifying theory, we cannot fully understand the origin of the universe or the true nature of spacetime at the smallest scales. The fact that our two most successful theories describe different aspects of reality yet cannot be combined remains one of the greatest paradoxes in science. Nowhere is this conflict more apparent than in black holes. A black hole is a region where gravity becomes so intense that nothing, not even light, can escape. As matter falls inward, it is compressed more and more tightly. According to Einstein's equations, everything ultimately collapses into a single point of infinite density known as a singularity. But infinities in physics usually signal a breakdown in our understanding. They suggest that the mathematics is being pushed beyond its limits. What truly exists at the center of a black hole remains unknown. Some physicists believe the singularity is real, a place where the known laws of physics simply fail. Others argue that a deeper theory, perhaps one that successfully merges quantum mechanics with gravity, will replace the singularity with something else. It might be a finite core, a looped structure of space-time, or an entirely new kind of object that cannot be described with our current concepts. The event horizon, the boundary of a black hole, prevents us from seeing inside. For now, the heart of a black hole is sealed off from observation and certainty, making it one of the most inaccessible mysteries in all of science. Closely related to this is our lack of understanding of singularities themselves. A singularity is a point where our equations predict infinite density, infinite curvature, and the collapse of space and time into something undefined. Black holes appear to contain them, and the Big Bang may have begun with one as well. But are singularities actual features of nature, or do they merely reveal the limits of our theories? Many physicists suspect they mark the boundary where Einstein's relativity bill breaks down. Beyond that boundary, a new framework must take over, one in which these infinities are replaced by something finite and well defined. Until such a theory is found, singularities remain puzzles at the edge of physics, places where our understanding stops and deeper reality remains hidden. Another unresolved mystery lies in the fate of information inside a black hole. When matter falls into a black hole, it appears to be lost forever. But according to quantum mechanics, information about a system's state should never be destroyed. This creates a serious conflict. What happens to the information carried by everything that crosses the event horizon? Stephen Hawking showed that black holes are not entirely black. They should slowly emit a faint form of radiation, now known as Hawking radiation, and eventually evaporate. But if a black hole disappears completely, what happens to the information it once contained? If the information is destroyed, one of the fundamental principles of quantum mechanics would be violated. If the information escapes, then it must somehow be encoded in the Hawking radiation through a mechanism we do not yet understand. This dilemma is known as the black hole information paradox, and it has challenged physicists for decades. Some theories suggest that information is stored on the surface of the event horizon itself. Others propose that black holes may connect to other regions of space-time, allowing information to escape in unexpected ways. Still others argue that our understanding of quantum mechanics may need to be revised at the deepest level. The question of what happens to information in a black hole is not just about black holes. It touches the foundations of reality itself. Hawking radiation is a powerful prediction, but it has never been directly observed. The signal is extraordinarily weak, far beyond our current ability to detect in space. And so, once again, we are left with a theory that points towards something profound, yet remains just out of reach. The universe continues to reveal its mysteries, slowly inviting us to keep asking questions even when the answers remain hidden. In the 1970s, Stephen Hawking made a remarkable prediction that changed how scientists think about black holes. According to his calculations, black holes are not perfectly dark. Quantum effects near the event horizon should cause them to emit a faint form of radiation, extremely weak but persistent, slowly draining their mass over immense spans of time. Given enough time far longer than the current age of the universe, a black hole could eventually evaporate completely. This predicted emission, now known as Hawking radiation, is one of the most famous ideas in modern physics. Yet it has never been observed directly. Real black holes are surrounded by swirling disks of superheated gas and violent environments that completely overwhelm any delicate signal Hawking radiation might produce. With today's technology, detecting it may simply be beyond our reach. Still, the implications of the idea are enormous. Hawking radiation links quantum mechanics, general relativity, and thermodynamics, three pillars of physics that rarely meet. It implies that black holes have a temperature, that they slowly lose energy, and that space-time itself is far more dynamic than once imagined. Scientists have attempted to create laboratory analogs of Hawking radiation using systems such as sound waves in fluids or light in special materials. These experiments offer intriguing hints, but they are only indirect simulations. Whether true Hawking radiation exists in nature remains unproven. If it does, it will profoundly reshape our understanding of black holes and the fundamental laws that govern them. If it does not, then something even stranger may be occurring at the edge of space-time. Because of these unknowns, black holes continue to push physics to its limits. Inside them, space and time curve and twist in ways our current theories cannot fully describe. Some mathematical solutions to Einstein's equations suggest that black holes could be connected to other regions of space-time through structures known as wormholes. In theory, falling into a black hole might lead somewhere else entirely. However, this idea remains highly speculative. Wormholes, if they exist at all, may be unstable, and the immense gravity of a black hole could destroy anything attempting to pass through. Even so, the mathematics leaves the door open. Some physicists propose that the singularity at a black hole's center could represent a bridge to a new universe, one with its own space and time. Others suggest that black holes might recycle information, playing a role in the creation of new cosmic regions. At present, none of these ideas can be tested. No signal can escape from within a black hole's event horizon, and so its deepest secrets remain hidden. Still, the possibility that black holes are more than cosmic endpoints, that they could be gateways to something beyond, remains one of the most captivating mysteries in science. Beyond black holes, another fundamental question remains unresolved: how the very first stars came into existence. In its earliest stages, the universe was a dark and simple place. There were no galaxies, no planets, and no complex elements. Only vast clouds of hydrogen and helium drifted through the expanding cosmos. At some point, these clouds collapsed under gravity, igniting nuclear fusion and giving birth to the first stars. This event ended the cosmic dark ages and flooded the universe with light for the first time. Yet the exact process that triggered this transformation is still not fully understood. These earliest stars, known as population 3 stars, were likely enormous, hundreds of times more massive than the Sun. They burned extremely hot and bright, but lived very short lives lasting only a few million years before exploding as powerful supernovae. In doing so, they forged the first heavy elements, seeding the universe with the materials needed for later generations of stars, planets, and eventually life itself. The challenge is that no population 3 star has ever been directly observed. They formed and died so quickly, so long ago, that no clear traces remain. Astronomers search for indirect evidence in the chemical signatures of ancient stars, hoping to find fingerprints left behind by these first stellar explosions. The James Webb Space Telescope may finally be powerful enough to glimpse their distant light or detect their influence. But for now, the precise mechanism that sparked the birth of the first stars remains one of the great open questions in astronomy. Another related mystery lies at the centers of galaxies. Nearly every large galaxy contains a supermassive black hole with masses millions or even billions of times greater than that of the Sun. We understand how black holes can grow over time by consuming gas stars and other black holes. Yet, when we look at the early universe, we find supermassive black holes that appear to have grown far too large, far too quickly. Their existence challenges our current models of cosmic evolution and suggests that something about their formation is still missing from our understanding. Some of these enormous black holes were already in place less than a billion years after the Big Bang. According to standard models of cosmic growth, there simply was not enough time for them to reach such immense sizes through gradual processes alone. This creates a serious puzzle. Did they form from the direct collapse of massive primordial gas clouds, bypassing the usual stages entirely? Did they originate from the deaths of the very first generation of stars, producing black holes far larger than expected? Or is there an unknown mechanism that allowed them to grow at extraordinary rates in the early universe? These ancient giants challenge our understanding of how galaxies evolve. If we can uncover how they formed so quickly, we may also uncover the story of how galaxies themselves came into existence. For now, they remain cosmic enigmas, massive objects that seem to appear far earlier than our theories predict. Another long standing mystery lies in the shapes of galaxies. When we imagine galaxies, we often picture graceful spirals with sweeping arms of stars winding outward like vast cosmic pinwheels. Our own Milky Way is one such spiral galaxy. Yet we still do not fully understand why spiral structures form at all. One idea proposes that spiral arms are not fixed structures, but density waves similar to traffic jams on a highway. Stars move through these regions briefly, crowding together and creating the appearance of persistent arms. Another theory suggests that spiral patterns arise from gravitational interactions as galaxies tug on one another, stirring stars into curved formations. Computer simulations can reproduce spiral shapes under certain conditions, but not consistently enough to explain all observed galaxies. Spiral galaxies are common throughout the universe, yet their origin, longevity, and stability remain unresolved. Why some galaxies develop elegant spiral arms while others become smooth elliptical systems is still an open question in astrophysics. When we look up at the night sky and see the Milky Way stretching across it, we are observing this mystery from the inside. Our home galaxy's familiar shape is both beautiful and unexplained. Far beyond our galaxy, another strange phenomenon flashes briefly across the universe. In 2007, astronomers detected a powerful burst of radio energy lasting only a few milliseconds. Since then, hundreds of similar events have been observed coming from distant galaxies in all directions. These events are known as fast radio bursts. Each one releases an enormous amount of energy comparable to what the sun emits over the course of an entire year, but compressed into an instant. The cause of these bursts remains uncertain. Some fast radio bursts repeat, suggesting they originate from ongoing processes such as magnetars, extremely dense neutron stars with intense magnetic fields capable of producing sudden flares. Others appear only once, hinting at catastrophic events like the collapse of a star or the merger of compact objects. No single explanation accounts for all of them. As these signals travel across billions of light years, they are distorted by the matter between galaxies. This distortion carries valuable information. By studying it, scientists can learn about the distribution of matter throughout the universe. In this way, fast radio bursts may serve as unexpected tools, helping us map the unseen structure of the cosmos even as their true origins remain unknown. But until their true origins are known, these signals remain unresolved cosmic riddles. From time to time, the universe sends us brief, powerful flashes across the emptiness of space. We can detect them. We can measure their strength and distance, yet we still do not know who or what is producing them. It is as if the cosmos is calling out, and we are listening without understanding the message. Pulsars offer another example of this strange precision. Pulsars are the collapsed remnants of massive stars, neutron stars, that spin rapidly while emitting narrow beams of radiation. As they rotate, these beams sweep across space like cosmic lighthouses. When discovered in 1967, their signals were so regular that scientists briefly considered whether they could be artificial. Today we know pulsars are natural objects, but their accuracy remains astonishing. Some pulsars rival or even surpass the precision of our best atomic clocks, spinning hundreds of times per second with extraordinary consistency. How an object so extreme a star, compressed into a sphere no larger than a city, can maintain such stability is still not fully understood. Their incredible density and intense magnetic fields play a role, but the detailed mechanisms remain unclear. Pulsars can also suddenly change their behavior, At times, they experience glitches, abrupt shifts in their rotation speed that defy prediction. These events may originate deep within their interiors, where superfluid matter behaves in ways unlike anything we can recreate on Earth. Pulsars serve as natural laboratories for extreme physics, yet many of their secrets remain hidden. Their steady rhythms continue to be among the most precise and mysterious signals in the universe. Even more extreme are magnetars. These are a rare type of neutron star with magnetic fields far stronger than any other known object. A magnetar's magnetic field can be thousands of times stronger than that of a typical neutron star and trillions of times stronger than Earth's. Such immense fields place enormous stress on the star itself. When that stress is released, magnetars erupt in sudden violent bursts of energy. In a single second, a magnetar can release more energy than the sun produces over tens of thousands of years. We observe these eruptions as intense flashes of X rays and gamma rays. What triggers them, however, remains uncertain. Some scientists believe the bursts are caused by starquakes fractures in the crust of the neutron star as magnetic forces twist and strain it. Others suggest the eruptions result from sudden rearrangements of the magnetic field snapping and reconnecting like a cosmic rubber band. Recent observations have linked at least some fast radio bursts to magnetars, suggesting they may explain part of that mystery. Still, magnetars do not account for everything. Only a few dozen are known, yet their power is staggering. They remind us that the universe contains engines of energy far beyond our everyday experience. Another mystery arrives constantly from above. Cosmic rays bombard Earth every second, carrying immense energy from distant regions of space. Most of these high energy particles are protons traveling at nearly the speed of light. Many originate from familiar sources, such as the sun or the remnants of exploded stars. But some cosmic rays are far more energetic than anything we can easily explain. The most extreme cosmic rays carry energies comparable to that of a fast moving baseball compressed into a single subatomic particle. No known process should be able to accelerate particles to such extraordinary speeds. Their origins remain uncertain. They may come from supermassive black holes, from the cores of active galaxies, or from exotic processes we have yet to discover. When these particles strike the Earth's atmosphere, they collide with atoms and create cascades of secondary particles that spread across large areas. Scientists detect these showers using vast observatories such as the Pierre Auger Observatory in Argentina, which monitors the skies in an effort to trace these particles back to their sources. Despite decades of observation, the most powerful cosmic rays remain unexplained, another reminder that the universe still holds forces and phenomena we do not yet fully understand. However, magnetic fields scattered throughout space bend the paths of these particles, scrambling the trails that might otherwise lead us back to their sources. Cosmic rays arrive at Earth, constantly silent messengers from distant regions of the universe. Yet their most extreme examples remain unexplained. They remind us that somewhere out there, nature operates particle accelerators far more powerful than anything humans have ever constructed. On the largest scales, The universe itself shows a strange and uneven structure. Matter is not spread smoothly through space. Instead, galaxies trace out a vast cosmic web, forming clusters and long filaments separated by enormous empty regions known as cosmic voids. Some of these voids stretch across hundreds of millions of light years and contain very few galaxies at all. Why such immense emptiness exists is still unclear. Computer simulations show that gravity naturally pulls matter into dense filaments, leaving emptier regions behind. But the largest voids appear even bigger than these models predict. This raises new questions. Do these vast empty regions point to unknown physics, perhaps related to how dark energy influences the growth of cosmic structure? Or are they simply rare statistical extremes, unlikely, but still possible within known laws? Cosmic voids also affect how light travels across the universe, subtly altering the signals we receive from distant galaxies. Because of this, they may offer clues about the nature of dark energy itself. For now, though, their true origin remains uncertain. Gazing into a cosmic void is like staring into nothingness on the largest possible scale. These regions are among the loneliest places in existence, vast stretches of space with no clear explanation for their size or shape. Equally uncertain is the ultimate fate of the universe. We know the cosmos had a beginning, but whether it will also have an end remains an open question. Scientists have proposed several possible futures, each determined by the behavior of dark energy and the balance of cosmic forces. In one scenario, the universe continues to expand forever gradually, cooling as stars burn out and galaxies fade away, leaving behind a cold, dark, and nearly empty cosmos. This outcome is often called the heat death of the universe. Another possibility is that the expansion could one day slow and reverse, pulling all matter back together in a catastrophic collapse. As the Big Crunch. A third scenario is even more dramatic. If dark energy grows stronger over time, it could eventually overcome all other forces, tearing apart galaxies, stars, planets, and ultimately even atoms in an event known as the Big Rip. Which of these futures awaits us is still unknown. Current observations suggest that expansion will continue, but the true nature of dark energy remains too uncertain to draw firm conclusions. The universe may persist for trillions of years, or it may end in a far more dramatic way. For now, the ultimate destiny of everything, stars, galaxies, and life itself remains one of the greatest unanswered questions in science. Even the universe's earliest moments are wrapped in mystery. Something appears to have triggered a brief but extraordinary period known as cosmic inflation. In the first fraction of a second after the Big Bang, space itself is thought to have expanded at an incredible rate, faster than the speed of light. This rapid expansion helps explain why the universe looks so smooth and uniform on large scales, and why tiny fluctuations grew into the galaxies we see today. Yet what caused inflation to begin remains unknown. Some theories propose the existence of a special energy field, often called the inflaton, which briefly dominated the universe before fading away. Others suggest that inflation may be rooted in the quantum structure of space-time itself. We can see hints of this process in the cosmic microwave background, where subtle patterns match what inflation predicts. Still, the true cause of inflation remains hidden, another reminder that even the earliest moments of the cosmos continue to resist full explanation. Yet the true cause of inflation, and even whether it unfolded exactly as our models describe, remains a subject of debate. Something caused the universe to expand at an unimaginable speed, setting the stage for everything that followed. But the force or mechanism that drove this expansion is still unknown, a missing chapter in the story of creation that science has not yet recovered. Closer to home, another mystery remains just as profound. The origin of life on Earth is still not fully understood. Life appears to have emerged more than 3.5 billion years ago, surprisingly soon after the planet cooled enough to support it. Fossil evidence shows that microscopic life was already widespread early in Earth's history. But how non living chemistry crossed the boundary into biology is still unclear. Several ideas attempt to explain this transition. One proposes that life began when simple molecules organized themselves into chains capable of storing information, perhaps using RNA before DNA ever existed. Another suggests that life emerged near hydrothermal vents on the ocean floor, where hot water minerals and chemical energy created a rich environment for complex reactions. A different possibility is that some of life's basic ingredients arrived from space, carried by comets or meteorites that struck the young Earth, delivering organic compounds from beyond our planet. Each of these ideas has experimental support, but none has been proven. Scientists have successfully produced amino acids and other essential molecules in laboratory conditions meant to resemble early Earth. However, creating a fully living system from these components remains far beyond our current capabilities. It is still unclear whether life's emergence was a rare and unique event or an inevitable outcome whenever the right conditions exist. Until stronger evidence appears, the moment when chemistry first awakened into biology remains one of the deepest mysteries in science. Even the location where life began is uncertain. Earth offered many possible environments capable of nurturing the first living systems. The vast oceans seem like a natural candidate. Hydrothermal vents provide constant energy and complex chemistry, and some researchers believe life may have started there with molecules assembling inside natural mineral structures. These compartments could have protected fragile chemical systems while allowing reactions to continue. Yet life may not have begun in the deep ocean at all. Some scientists argue that shallow pools on land, repeatedly drying and refilling, could have concentrated molecules and driven crucial chemical reactions. Sunlight, especially ultraviolet radiation, may have supplied the energy needed to power these processes, even though it can be destructive under other conditions. Both environments offer plausible pathways, and both present serious challenges. Oceans tend to dilute molecules, making interactions less likely, while land-based pools may have been too unstable to sustain long-term chemistry. For now, we do not know whether life first stirred beneath the sea or in sunlit waters on land. The answer lies buried in rocks and traces that have been transformed by billions of years of geological change. We also do not yet understand how the first living cells formed. Life is not defined by chemistry alone, but by organization. Modern cells are highly structured systems enclosed by membranes and filled with molecular machines performing countless coordinated reactions. How such complexity arose from simple chemistry remains unknown. One possibility is that fatty molecules naturally present on the early Earth formed tiny bubbles that trapped useful chemical reactions inside. These primitive membranes could have protected fragile molecules like RNA while still allowing energy and materials to pass through. Experiments show that such simple membranes can form spontaneously under the right conditions. Over time, the chemistry inside these compartments may have grown more complex, eventually becoming self sustaining. Still, the leap from these primitive structures to a fully functioning living cell remains unexplained. The transition from disordered chemistry to organized life is one of the great unsolved problems in biology. Until it is understood, the true beginning of life remains hidden. Even at the molecular level, mysteries persist. All known life on Earth uses DNA to store information, and DNA has a very specific structure. Why life settled on this particular molecule and this particular shape rather than countless other possibilities is still unknown. The fact that every organism shares this same molecular language suggests a deep and ancient choice made at the dawn of life, a choice whose origin we have yet to explain. Its double helix structure is elegant and universal, carrying the instructions that shape every organism on Earth. Yet this raises a deeper question. Why this molecule and why this specific form, chemistry, allows many possible ways to store information. RNA, for example, is simpler and may have played a central role early in life's history. At some point, however, DNA became the primary molecule for storing genetic information. Its stability, its ability to replicate with high accuracy, and its capacity to encode vast amounts of information made it exceptionally effective. Still, we do not know why this particular structure, with its paired bases and twisted ladder shape, became the foundation of all life. Was this outcome inevitable, dictated by the laws of chemistry, or was it a historical accident, one successful solution among countless alternatives that failed? The fact that all known life uses DNA suggests that it may be the most efficient answer nature could find. Even so, the reason life followed this exact path remains unknown, pointing to deeper mysteries within the chemistry that underlies existence itself. The origins of viruses add another layer of uncertainty. Viruses occupy a strange position between life and non life. They cannot reproduce independently and must rely on the machinery of living cells, yet they are not inert. They evolve, adapt, and profoundly influence the course of life on Earth. Where viruses came from is still unclear. Some scientists think they are remnants of an ancient RNA based world, survivors from a time before fully formed cells existed. Others propose that viruses began as fragments of genetic material that escaped from cells and developed the ability to replicate. A third idea suggests that viruses may be the descendants of once living organisms that became simplified over time. The truth may involve more than one origin. Viruses could have emerged through multiple pathways, their diversity reflecting the complexity of life itself. What is clear is that viruses are ancient, and they may have played a crucial role in evolution by transferring genes between organisms and driving genetic innovation. By blurring the boundary between living and non living systems, viruses challenge our definitions of life and remain one of biology's most enduring mysteries. This leads to a more fundamental to the question. Among countless molecules present on the early Earth, why did some become alive while others did not? The young planet was rich in chemistry. Simple molecules formed in many environments, from deep sea vents to volcanic landscapes and lightning filled atmospheres. Many of these molecules combined into more complex structures, such as amino acids and nucleotides. Yet only a tiny fraction of this chemical activity crossed the threshold into life. What special properties allowed certain molecules to organize into systems capable of self replication and evolution was the emergence of life, an inevitable result once the right ingredients were present. Or was it a rare accident dependent on a sequence of unlikely events? Laboratory experiments show that many of life's building blocks can form under natural conditions. But creating a self sustaining, evolving system remains an unsolved challenge. The jump from chemistry to biology is vast, and we still do not understand how it was made. This uncertainty carries profound implications. If life arises easily whenever conditions allow, then the universe may be filled with living worlds. If it was a rare fluke dependent on chance, then life on Earth may be exceptionally uncommon. The question of why some molecules became alive while others remained inert stands among the most important unanswered questions in science. And beyond Earth, the mystery only deepens. We still do not know whether life exists anywhere else in the universe. So far, our planet is the only place where life has been confirmed. Whether life is widespread or rare, beyond Earth remains unknown, leaving us to wonder how unique our own existence truly is. With hundreds of billions of stars in our galaxy, alone and countless galaxies beyond it, it seems reasonable to suspect that we are not alone. And yet, despite decades of careful searching, no clear evidence of life beyond Earth has been found. Astronomers have discovered the thousands of planets orbiting other stars, many of them located in regions where liquid water could exist. We know that organic molecules are widespread in space, detected on comets in interstellar clouds and on distant moons. Mars bears signs of a wetter past, while moons such as Europa and Enceladus conceal vast oceans beneath layers of ice. On paper, the conditions for life appear abundant, and still the universe remains silent. We have not detected artificial signals, found microbial life on Mars, or uncovered unmistakable traces of alien biology. It is possible that life is common, but difficult to detect it hidden beneath surfaces or spread thinly across vast distances. It is also possible that life is exceedingly rare, requiring a combination of conditions we do not yet fully understand. Until we discover even the simplest form of life beyond Earth, the question of whether life exists elsewhere remains unanswered. Another layer of uncertainty lies in the nature of life itself. Could life arise from chemistry entirely different from our own? All known life on Earth shares the same basic ingredients: carbon based molecules, liquid water, DNA, and proteins. But it is not clear whether this is the only possible solution. Some scientists speculate that silicon, which can form complex structures and is abundant in the universe, might serve as the foundation for alien life. Others imagine organisms that use ammonia instead of water or life forms adapted to methane rich environments like those on Saturn's moon Titan. More speculative ideas suggest that entirely unfamiliar systems involving plasma magnetic fields or even information itself could display lifelike behavior. At present, we simply do not know. Every definition of life we use is shaped by a single example: life on Earth. It may be that carbon and water are uniquely suited to support living systems, or it may be that the universe hosts forms of life so unfamiliar that we have not yet learned how to recognize them. If we do one day encounter an alien life, it may challenge our deepest assumptions about what it means to be alive. Even the number of truly habitable worlds remains uncertain. Thousands of exoplanets have been identified, many of them small and rocky, some located in the so called habitable zone of their stars. But habitability depends on far more than distance alone. A planet must have the right atmosphere protection from harmful radiation, geological stability, and long term conditions that allow chemistry to persist. Some planets may be stripped bare by radiation, while others may freeze without sufficient heat. Moons, too, could be habitable, especially those with subsurface oceans, but we cannot yet study them in detail. The galaxy may be filled with worlds capable of supporting life, or such worlds may be rare and fragile exceptions. At present, we cannot say. Each new discovery brings us closer to an answer, but the true frequency of Earth like conditions remains one of the great open questions in astronomy. And so we return to the oldest question of all: are we alone? For as long as humans have gazed at the night sky, we have wondered whether life exists beyond our planet. Despite the vastness of the universe, the abundance of planets, and the widespread chemistry of life, we still have no definitive answer. We listen for signals with radio telescopes. We send robotic explorers to planets and moons. We analyze the atmospheres of distant worlds, searching for subtle signs of biology. So far, the silence remains unbroken. It may be that life is common, but intelligent civilizations are rare or short lived. It may be that life itself is extraordinarily rare, and that we are the result of a singular chain of unlikely events. Or it may be that life is widespread, but hidden from us by distance, time, or forms we do not yet recognize. Until evidence emerges, the question remains open. Are we a lone spark in a vast and empty cosmos, or one quiet voice in a universe filled with unseen life? for now, the answer remains unknown. Consciousness appears to arise from the brain, yet how this happens remains unknown. Every thought, every memory, every moment of awareness seems tied to activity inside the brain. Scientists can record electrical signals moving through networks of neurons. They can turn consciousness off with anesthesia and watch it gradually return. They can even map which areas of the brain become active when you see an image, hear a sound, or focus your attention. And yet, none of this explains why there is an inner experience at all. A brain scan may show activity in the visual cortex when you look at a sunset, but it does not explain why that activity becomes the experience of glowing reds and soft golds inside your mind. It can show circuits responding to sound, but it cannot explain why a familiar song stirs emotion or memory. Many theories attempt to bridge this gap. Some suggest that consciousness emerges when information is shared across the brain in complex ways. Others propose that specific neural patterns give rise to awareness. More radical ideas suggest that consciousness may be a fundamental feature of reality itself, not something created by matter, but something matter can express. Still, none of these ideas fully explain how physical processes turn into subjective experience. Consciousness is the most ordinary thing we know. It is what you are experiencing right now. And yet, when we try to define it or explain it, it slips away. We know it depends on the brain, but how matter gives rise to mind remains one of the deepest mysteries in science. Dreams add another layer to this mystery. Every night as you sleep, your mind creates entire worlds. Some dreams feel familiar, filled with people and places from your life. Others are strange, fragmented, and difficult to remember once you wake. Despite how common dreams are, no one truly knows why we have them. Some scientists believe dreams help the brain rehearse experiences, replaying memories, and strengthening useful connections. Others think dreams play a role in emotional balance, allowing the mind to process fear, stress, or unresolved feelings in a safe, imagined space. Another view suggests dreams are the result of random neural activity during sleep woven into stories by the brain. What makes dreams especially puzzling is their emotional power. A nightmare can leave you shaken even though your body is safe in bed. A pleasant dream can influence your mood long after you wake. Sometimes dreams even lead to insight. Writers, artists, and scientists have all described moments when a solution or creative idea appeared during sleep. We know the brain remains highly active during dreaming, particularly during rapid eye movement sleep, when the eyes move beneath closed lids. But the deeper purpose of dreaming remains unclear. Dreams are familiar nightly journeys into imagined worlds, yet their true function is still hidden. Our experience of time is just as mysterious. Time itself flows steadily, but our perception of it does not. Think of moments when time seemed to slow down during a sudden shock danger or intense focus. Then think of times when hours passed without notice, perhaps during a holiday or while doing something you love. The clock moves at a constant pace, but the mind does not experience it that way. Neuroscience has not yet explained why our sense of time stretches and compresses depending on emotion, attention, and state of mind. The brain does not contain a single clock. Instead, time perception appears to emerge from many processes working together. Memory, attention, and emotion all shape how long a moment feels. When the brain is overloaded with new information, time can feel longer. When it is deeply absorbed, time can seem to vanish. Why this happens remains uncertain. Our experience of time is flexible, subjective, and deeply tied to consciousness itself. Why this happens is still uncertain. Some researchers believe the brain contains internal timing mechanisms and that emotions influence how fast or slow this internal clock feels. States like fear or urgency may accelerate our sense of time, while calm or focused states may slow it down. Others suggest that the brain estimates time based on how much information it processes. Moments filled with new experiences feel longer, while familiar routines seem to pass quickly. This may explain why childhood summers felt endless, while adult years appear to slip by with surprising speed. Novelty stretches time in the mind, while repetition compresses it. Yet this remains a theory, not a complete explanation. What we do know is that psychological time is flexible. It expands, contracts, and sometimes feels as if it stops altogether. Seconds and minutes remain constant, but our experience of them follows rules we do not yet fully understand. Memory presents another deep mystery. Everything you have lived through, your earliest memories, your happiest moments, your quiet regrets, is somehow stored within your brain. But how those experiences are encoded and later retrieved remains unclear. Scientists know that memories are not stored like files in a cabinet. Instead, they are patterns of activity distributed across networks of neurons in different regions of the brain. The hippocampus appears to play a key role helping organize and link these patterns, acting somewhat like an index. Still, the precise process by which the brain records a memory and later reconstructs it is not fully understood. Memories are also not fixed. Each time we recall one, it can change slightly before being stored again. In some cases, entirely false memories can form yet feel just as real as genuine ones. Why some memories remain vivid for a lifetime while others fade within days is still unknown. A particular scent can suddenly unlock a detailed scene from childhood, complete with emotion and imagery. Experiments have revealed individual neurons that respond to specific faces or places and patterns of brain activity that resemble memory recall. But these findings are only pieces of a much larger puzzle. Memory is what gives us a sense of identity over time, and yet the mechanisms behind it remain largely hidden. Emotions deepen this mystery even further. They shape nearly every aspect of our lives. Joy motivates us, fear protects us, anger energizes, sadness slows us down. But where emotions truly come from is still debated. We know emotions involve both the brain and the body. The heart races in fear, the stomach tightens in anxiety, tears appear in sadness. But scientists still argue over whether emotions are hardwired biological programs shaped by evolution or whether they are constructed by the brain using context memory and cultural meaning. Certain brain regions are clearly involved. The amygdala plays a role in fear, the insula in bodily awareness, and the prefrontal cortex in emotional regulation. Yet there is no single center for any emotion. Music can suddenly cause goosebumps. A familiar scent can trigger powerful nostalgia. Sometimes we experience the strong feelings without knowing why. Emotions guide our decisions often more powerfully than logic, yet the way they arise and take hold of both body and mind remains one of the most intimate mysteries of human experience. Creativity adds yet another unanswered question. Ideas often appear suddenly, without warning. An artist faces a blank canvas, a writer, an empty page, a scientist, an unsolved problem, and nothing happens for a long time. Then, unexpectedly, an idea arrives complete and vivid. Where did it come from? Creativity feels like a spark, but its source is hidden. Some theories suggest it emerges from the brain, combining existing ideas in new ways. Others propose that creativity requires letting go, allowing subconscious processes to work while conscious effort rests. We can observe the brain during creative tasks, but the moment when an idea is born remains elusive. Many of the greatest breakthroughs in history did not occur at desks or in laboratories, but during dreams, quiet walks, or moments of rest. Brain imaging studies suggest that creativity involves multiple neural networks, some responsible for generating ideas and others for evaluating them. Yet this still does not explain the suddenness of inspiration. Why does a solution sometimes arrive all at once, complete and unmistakable? Why do some minds seem to overflow with ideas while others struggle to produce them? Creativity is one of humanity's most powerful abilities, shaping art, science, and progress itself. And yet, the place where ideas originate, the silent leap from nothing into something meaningful, remains a mystery we cannot yet explain. Another strange experience of the mind is deja vu. You step into a situation you know is new, yet it feels oddly familiar, as though you have lived it before. For a brief moment, the present seems to echo the past. Scientists have proposed several explanations. One idea is that deja vu arises from a memory glitch, where the brain mistakenly signals familiarity without an actual memory to support it. Another suggests that it occurs when different parts of the brain process the same experience at slightly different times, creating the illusion that the moment is being repeated. Others believe it may result from subtle similarities between a current experience and a forgotten one, misleading the brain into a false sense of recognition. What makes deja vu especially unsettling is its intensity. For a few seconds, reality feels doubled, both new and remembered at once. Nearly everyone experiences it at some point, yet no one can predict when or why it will happen. Deja vu reminds us that memory and perception are fragile and that the brain can momentarily mislead us in ways we do not yet understand. The power of the mind over the body appears again in the placebo effect. A person takes a pill they believe will help, and their symptoms improve, even when the pill contains no active medicine. This effect has been observed to reduce pain, ease depression, and even alleviate some symptoms of neurological disorders. Expectation seems to play a central role. Belief alone can trigger real changes in the brain, releasing natural pain relieving chemicals, altering brain activity, and influencing the immune system. What makes the placebo effect especially puzzling is that it can sometimes work even when people know they are receiving a placebo. The ritual of treatment, the act of care, and the expectation of healing appear to activate hidden pathways within the body. Yet not everyone responds the same way. Why some individuals are highly sensitive to placebo effects, while others feel nothing, remains unknown. The placebo effect blurs the boundary between mind and body, revealing that belief itself can influence physical reality in ways science does not yet fully understand. Sleep presents another profound mystery. Every night we surrender consciousness and drift into sleep, remaining unaware for hours. From an evolutionary perspective, sleep seems dangerous. A sleeping animal is vulnerable, and yet nearly every species sleeps in some form. This suggests that sleep serves a vital purpose. But what exactly is that purpose? Some scientists believe sleep helps consolidate memories and support learning. Others think it allows the brain to clear metabolic waste, effectively cleaning itself. Sleep may restore energy, regulate emotions, strengthen the immune system, and help maintain healthy neural connections. Still, no single explanation fully accounts for all the evidence. Different animals sleep in remarkably different ways. Dolphins allow only half of their brain to sleep at a time. Some birds sleep while flying. Other species need surprisingly little sleep. What is certain is that without sleep, both mind and body quickly deteriorate. Why we spend nearly a third of our lives asleep remains one of the great unsolved questions in science. Aging adds yet another layer of mystery. Every living organism grows older, but science cannot fully explain why aging happens the way it does. Skin wrinkles muscles, weakened cells lose function, and eventually the body begins to fail. Yet aging unfolds very differently across species. Some animals live only days, while others live for centuries. One explanation points to our DNA. Over time, genetic material accumulates damage. Cells divide, telomeres shorten, and repair mechanisms slowly become less effective. But this is only part of the story. Other theories suggest aging arises from accumulated cellular stress, metabolic byproducts, or changes in the way genes are regulated. Some organisms appear to resist an aging remarkably well, raising the question of whether aging is inevitable or simply a side effect of how life evolved. Why the body does not repair itself indefinitely, and why aging follows such different paths across life. Forms remains unresolved. Each time a cell divides, the protective caps at the ends of chromosomes known as telomeres become slightly shorter. Eventually, these caps wear down to the point where the cell can no longer divide. This process is thought to contribute to aging at the cellular level. Another explanation focuses on damage. Over time, reactive molecules produced by normal metabolism slowly injure cells, leaving behind microscopic scars that accumulate year after year. A different perspective views aging as an evolutionary trade off where energy is invested in growth and reproduction early in life, while long term maintenance is sacrificed, leaving the body increasingly vulnerable with age. Yet nature does not follow a single rule. Some turtles and fish show little evidence of aging even late in life. Certain jellyfish appear capable of reversing their life cycle, returning to an earlier developmental stage instead of dying. Naked mole rats live far longer than expected for their size and show remarkable resistance to cancer and age related disease. Why some species seem to escape aging while humans do not remains unclear, and why aging in our own bodies follows such a predictable path is still an open question. Unlocking this mystery could transform medicine, but for now, aging remains a riddle written deep within our cells. The limits of the human lifespan are also uncertain. The longest verified human life reached 122 years, but whether this represents a true biological ceiling or an extraordinary exception is unknown. Some scientists argue that humans have a hard upper limit beyond which the body can no longer repair itself fast enough to survive. Survival rates drop sharply after the age of 110, suggesting a biological boundary. Others believe there is no fixed maximum, only increasing vulnerability to disease injury and chance as age advances. What makes this puzzle even more intriguing is that while average life expectancy has risen dramatically due to advances in medicine, hygiene, and nutrition, the maximum human lifespan has barely changed. Very few people live beyond 115 years, regardless of era or location. Still, researchers continue to search for ways to extend life. They study families with unusually long lived members, examine genes linked to resilience, and test treatments that slow aging in animals. Whether humans could one day live 150 years or even longer remains uncertain. The upper boundary of human life is still hidden, waiting to be discovered. Regeneration presents another striking mystery. In many species, lost body parts can grow back. Salamanders can regenerate entire limbs. Starfish can rebuild lost arms. Some simple organisms can regenerate a whole body from a single fragment. In humans, regeneration is extremely limited. A child's fingertip may partially regrow, but a lost limb never returns. Why this ability exists in some creatures but not in us remains unexplained. Studies of salamanders show that when they are injured, nearby cells revert to a flexible, almost embryonic state. From there, they reorganize and grow into muscles, bones, nerves, and skin perfectly structured and functional. Humans possess many of the same genes involved in these processes. Yet, for reasons we do not understand, our bodies do not activate them in the same way. If this ability could be unlocked, medicine would change completely. Damaged hearts might repair themselves. Spinal cords could regrow. Lost limbs might return. Despite decades of research, the full instructions for regeneration remain hidden. Why nature grants this power to some species while withholding it from us remains a profound mystery. Longevity itself defies simple rules. In general, small animals tend to live short lives, while larger animals live longer ones. Mice live only a few years. Elephants can live for many decades. Humans, with our relatively long lifespan, are already unusual among primates. But there are exceptions that challenge even this pattern. Some small animals live surprisingly long lives, far exceeding expectations based on size alone. Why these creatures age so slowly, and why humans fall somewhere in between remains another unanswered question in the biology of life. Scattered throughout nature are creatures that seem to ignore the usual rules of aging altogether. The Greenland shark moves slowly beneath the Arctic ice, living for centuries with lifespans estimated to exceed 400 years. Bowhead whales sing in frozen seas for more than 2 centuries. Tiny naked mole rats, no larger than a mouse, live nearly 10 times longer than similar rodents and show an extraordinary resistance to age related decline. Some clams have been found alive after more than 500 years. These animals challenge everything we think we know about lifespan. Scientists have uncovered clues, but not complete answers. Some of these species possess unusual proteins that resist damage. Others appear to have exceptionally efficient DNA repair systems. Many share extremely slow metabolisms that reduce wear over time. Yet no single explanation fits them all. Each species seems to hold its own solution to longevity written into its biology in a unique way. Humans cannot yet copy these strategies. Still, these long lived creatures remind us that aging is not an unbreakable law of nature, but a complex puzzle with many possible outcomes. If we could learn their secrets, we might one day find new ways to extend healthy human life. For now, they remain quiet enigmas of the living world. Some animals also survive conditions that should mean instant death. Imagine being frozen solid blood, crystallized heart stopped, body locked in ice. For most life, this would be the end. Yet the wood frog of North America endures exactly this each winter. Its heart stops beating, its body becomes rigid, and when spring arrives, it thaws, breathes, and hops away as if nothing happened. Certain insects and fish possess similar abilities. Even more extreme are tardigrades, microscopic creatures that can survive freezing, boiling, intense radiation and even the vacuum of space. How these organisms endure such extremes remains only partially understood. Some fill their bodies with antifreeze like molecules that prevent ice crystals from tearing cells apart. Others rely on sugars that stabilize tissues during freezing and dehydration. But how delicate organs like the brain and heart survive months without activity is still unclear. If humans could master this ability, it could transform medicine. Organs might be preserved for long periods. Emergency treatments could change completely. Even deep space travel might one day involve forms of human hibernation. For now, this remarkable power belongs only to these resilient survivors creatures that seem to bend the boundary between life and death. Longevity without disease presents another mystery beneath the waves. Bowhead whales can live for more than 200 years swimming through icy waters with little sign of cancer. This is astonishing not only because of their age, but because of their size. With trillions of cells and centuries of time for mutations to accumulate, whales should in theory face enormous cancer risk. Yet they do not. This contradiction is known as Peto's paradox. Larger animals with more cells should have higher cancer rates, but whales, elephants, and other giants largely avoid this fate. In elephants, researchers have discovered extra copies of tumor suppressor genes, providing additional layers of protection. In whales, the explanation is less clear. Their DNA repair systems may be unusually powerful. Their metabolism may reduce cellular damage, or they may rely on biological pathways we have not yet identified. If these mechanisms could be understood, they might revolutionize how humans prevent or treat cancer. Whales appear to have solved part of the puzzle of long life, without disease, but their secret still drifts silently beneath the ocean's surface. Birds introduce another mystery of nature. Every year they migrate across vast distances, navigating continents and oceans with astonishing accuracy. Somehow, birds can sense Earth's magnetic field and use it as a guide. Yet the exact mechanism behind this ability remains unclear. Some theories suggest specialized proteins in their eyes respond to magnetic fields. Others propose microscopic magnetic particles embedded in their tissues. Despite decades of research, how birds perceive an invisible force that humans cannot feel remains unresolved. Tiny warblers travel from Europe to Africa each year, crossing deserts and seas with remarkable accuracy. Arctic terns take this even further, flying across oceans and circling the globe during their lifetime. These journeys span thousands of miles, yet the birds rarely lose their way. Part of their ability appears to involve Earth's magnetic field, but how they detect it is still uncertain. Some studies suggest microscopic crystals of magnetite inside their bodies may function like internal compasses. Other research points to specialized proteins in their eyes that could allow birds to perceive magnetic fields as faint visual patterns. No single explanation accounts for everything. What is clear is the precision of their navigation. Even on cloudy days, when the sun and stars are hidden, birds remain on course. Released in unfamiliar territory, they still orient themselves and head in the correct direction. It is a sensory layer of reality. Humans do not possess an invisible map woven into the world itself. Monarch butterflies follow a map that seems even more mysterious. Each autumn, delicate monarchs begin an extraordinary migration, flying from Canada and the northern United States to a small region of forest in central Mexico. Their millions gather, covering trees in waves of orange. What makes this journey especially astonishing is that no single butterfly completes the full round trip. The butterflies that return north in spring are several generations removed from those that left in the fall, yet they arrive at the same mountains, the same forests year after year. Scientists know monarchs use the sun as a compass adjusting for the time of day, and they may also sense Earth's magnetic field. But how this directional knowledge is passed across generations remains unknown. How a butterfly that has never made the journey knows exactly where to go is still unexplained. Across the natural world, Long distance migration is common. Salmon hatch in mountain streams, travel to the open ocean, and years later return to the very same waters to spawn. Sea turtles cross entire oceans and come ashore on the same beaches where they were born. Birds, whales, and insects traverse continents and seas with astonishing reliability. Scientists have uncovered pieces of the puzzle. Some animals navigate using the sun, the stars, or the tilt of Earth's axis. Others may rely on magnetic fields, chemical cues, or subtle environmental signals. Still, none of these explanations fully account for the accuracy of these journeys. How a bird finds the same tree each year, or how a turtle returns to one stretch of sand after decades at sea, remains partly unknown. Migration is one of life's oldest rhythms, a vast and mysterious choreography written into instinct. Homing pigeons provide another example of this unexplained precision. For centuries, humans have been fascinated by their ability to return home from unfamiliar places. Release a pigeon hundreds of miles away, and it will circle briefly before flying straight back to its loft. There is no visible map, no clear guide. Researchers have proposed many explanations. Some suggest pigeons use the sun as a compass adjusting for time of day. Others believe they sense Earth's magnetic field functioning like a natural navigation system. Additional theories propose that pigeons may use subtle cues, such as low frequency sounds, carried over long distances, familiar smells, or even visual landmarks learned during earlier flights. Experiments have shown that disrupting one sense often does not completely confuse them, suggesting that pigeons rely on multiple overlapping systems. How the brain combines all of this information into a single sense of direction remains unclear. Despite decades of study, the full mechanism behind their homing ability has not been revealed. These navigating animals remind us that the natural world is filled with senses beyond our own. Directions may be written into the environment in ways we cannot perceive. For birds, butterflies, turtles, and pigeons, the planet itself seems to offer guidance, a silent language of fields, patterns, and signals that we are only beginning to glimpse. How these hidden maps work and how life learned to read them so precisely remains one of nature's quietest and most enduring mysteries. Others suggest that smell plays a role, proposing that pigeons construct a detailed scent map of their home region and use it to navigate back. But even this explanation falls short. Pigeons released in unfamiliar locations under overcast skies and far beyond known territory still manage to return home with astonishing precision. Their navigation seems to rely on a combination of cues woven together in ways we do not yet understand. Somewhere within their biology lies a hidden compass, a system so reliable that it continues to defy explanation. For pigeons, the world appears filled with invisible signals that guide them through the sky. For humans, this ability remains an unsolved puzzle. Equally mysterious is the origin of human language. Language is central to what makes us human. Through it, we share ideas, preserve memories, and build entire cultures and civilizations. Yet no one knows exactly how language first emerged. Our closest living relatives, chimpanzees and bonobos, communicate using gestures, expressions, and sounds, but their systems fall far short of the complexities of human speech. At some point in our evolutionary past, our ancestors crossed a threshold, moving from simple calls to structured language, complete with grammar, abstraction, and limitless expression. When and how this transformation occurred is still debated. Some theories suggest that language began with gestures, with spoken words developing later. Others propose that rhythmic sounds, chants, or musical vocalizations gradually evolved into speech. Archaeological evidence shows symbolic art carvings and tools tens of thousands of years old, indicating minds already capable of complex thought and communication. But spoken language itself left no physical trace. Sounds fade, leaving no fossil record. Language allows us to talk about what is not present, to plan for the future, to imagine things that do not yet exist. It is both a tool for survival and a window into the human mind. Yet the first spark of language, the moment when early humans first spoke in structured ways, is lost to time. We can only imagine the earliest conversations that set everything else in motion. Laughter presents another universal mystery. Across cultures, ages, and societies, humans laugh. Infants laugh long before they learn to speak. Groups laugh together, the sound spreading easily from one person to another. Yet why we laugh and how it evolved is still unclear. Some researchers believe laughter began as a signal of safety, a way to show that danger had passed and tension could be released. Others trace its roots to play behavior in primates whose rhythmic panting during wrestling and chasing closely resembles human laughter. But laughter goes beyond survival. It strengthens social bonds, reduces stress, and releases powerful chemicals in the brain that promote calm and connection. We laugh at jokes, but also at relief awkward moments, and sometimes even in situations of sadness or shock. At times, laughter bursts out when it seems to make no sense at all. Why a simple sound, a breathy rhythm of air carries such emotional power remains unknown. What we do know is that laughter is ancient, shared by all humans, and deeply woven into social life. It connects us instantly, often without words. And yet, its true origin and purpose remain another quiet mystery of being human, familiar to everyone, fully understood by no one. It is the quiet music of joy shared across all of humanity, its origins buried deep in our past. Music moves us in ways that science still struggles to explain. A simple melody can bring tears. A steady rhythm can quicken the heartbeat. A familiar song can unlock memories we believed were lost forever. Music has no obvious survival function, yet it exists in every known culture and plays a central role in human life. Why this is so remains unclear. Some researchers believe music evolved as a social bond, a way for early communities to synchronize through rhythm movement and shared sound. Others suggest it began as a form of courtship, signaling health coordination or creativity. Another view is that music is a byproduct of language and memory, an accidental gift emerging from brains already tuned for communication. None of these explanations fully capture music's power. What makes music especially mysterious is how deeply it reaches into the brain. People who have lost the ability to speak after a stroke can still sing. Individuals with advanced dementia may remember song lyrics long after names and faces have faded. Music can synchronize heartbeats in groups, soothe infants, and stir crowds into collective motion. Why organized sound can affect emotion, memory, and even the body so directly remains unknown. Music seems to bypass logic and speak to something deeper. It remains one of the most universal and unexplained forces in human experience, an invisible thread connecting minds across time. Love is another force that shapes human life more than almost anything else, yet its full nature remains elusive. Love binds parents to children, partners to one another, friends across years and distance. It inspires sacrifice, creativity, and meaning. Biology explains part of it. Love floods the brain with chemicals linked to pleasure attachment and trust. Evolutionary theories suggest it helped keep caregivers together long enough to raise vulnerable offspring. But these explanations feel incomplete. They do not explain why love can arrive suddenly and powerfully, or why it endures for decades in some lives and fades quickly in others. They do not explain why people risk everything for it sometimes against reason or self interest. Love is not only chemistry or instinct, it is memory, story, imagination, and shared meaning. Science can map what love does in the brain, but not what it feels like from the inside. Love is universal, yet deeply personal, a shared human experience that is never exactly the same twice. Its full nature remains one of the deepest mysteries of being alive. Humans also cry emotional tears, and no one fully understands why. Tears protect the eyes, washing away dust and salt. But only humans shed tears in response to emotion, whether sadness, joy, frustration, or overwhelming relief. One idea suggests tears act as a social signal, making vulnerability visible and drawing empathy from others. Another proposes that crying helps regulate stress by releasing certain chemicals, though evidence remains mixed. What deepens the mystery is that tears appear in opposite emotional states. We cry from grief and from happiness, from loss and from release. Tears fall quietly in solitude or spill out during laughter. No single explanation accounts for all of this. Tears remind us that humans are not purely rational beings. They turn inner experience outward, making emotion visible. Why this response evolved only in humans remains unknown, a secret carried in every tear that falls. Across cultures, another mystery repeats itself. Myths arise in strikingly similar forms in societies separated by oceans and centuries. Stories of great floods, sky gods, tricksters, journeys to the underworld, and rebirth appear again and again. Some believe the human mind is naturally drawn to certain themes shaped by shared fears and hopes: death, renewal, chaos, and order. Others suggest ancient stories spread through migration and trade, leaving echoes across distant lands. Another possibility is that myths emerge from deep patterns in the human brain's symbols shaped by a shared inner landscape. Whatever their origin, myths carry meaning. They help people explain the unknown bind communities together and pass values and wisdom from one generation to the next. They are stories humanity tells itself to make sense of existence. And why these stories take such similar forms across the world remains one more unanswered question woven quietly into the human story. Yet the strange repetition of similar stories across distant cultures, appearing where no direct contact seems possible, remains unexplained. We also carry another quiet mystery within us, our instinct to cooperate with strangers. Humans are unusual among animals. We do not only care for family or close allies, we help people we have never met. We donate blood build communities and sometimes risk our lives for others without expecting anything in return. Why do we do this? Evolution offers partial answers. Cooperation may have helped early groups survive, giving them strength against rivals. Reciprocal altruism suggests that helping others increases the chance of being helped later. But human kindness often goes beyond calculation. We give even when no reward is likely. Experiments show that very young children choose to help others before they fully understand rules, culture, or social expectation. Something in us seems naturally drawn toward cooperation. Whether this impulse arose purely from survival pressures or from a deeper moral instinct written into the human mind remains unclear. Our willingness to help strangers is one of humanity's most beautiful traits and also one of its most mysterious. Human societies themselves follow patterns we still struggle to understand. Across history, great civilizations have risen, flourished, and then fallen. The Maya, the Indus Valley, Mesopotamia, Rome, each reached remarkable heights before collapsing. Why this happens remains debated. Some point to climate shifts, droughts, and natural disasters. Others emphasize war, inequality, corruption, or the exhaustion of resources. Still others believe civilizations follow repeating cycles of growth and decline patterns that unfold regardless of era or location. What is most striking is how sudden collapse can be. Thriving cities are abandoned, knowledge is lost, entire cultures fade into silence. Civilization is more fragile than it appears, and the forces that sustain it or bring it down are not fully understood. We live inside complex systems built over generations, yet history reminds us that nothing lasts forever. Why some societies endure while others vanish remains an open question. Underlying all of this is another quiet force: human curiosity. Why do we wonder? Why do we look up at the stars and ask questions? No other creature seems to ask. Curiosity defines us. Yet its origin is still unknown. Some believe curiosity evolved as a survival tool, helping us explore environments, find food, and avoid danger. Others argue it became an evolutionary advantage, driving innovation, exploration, and learning. But curiosity often goes far beyond survival. It leads us to study galaxies billions of light years away, to decode ancient languages, to ask questions with no immediate practical value. Children show curiosity from the very beginning, reaching for the unfamiliar, asking endless questions. It seems built into us. Why this hunger to understand exists, why the mind is restless for answers, remains unexplained. Curiosity pushes science forward, fuels art, and drives exploration. Yet the spark behind the simple question, why, is still a mystery. Storytelling is another universal human behavior whose purpose we do not fully understand. Every culture tells stories around fires, on stages, in books, and through screens. Humans shape experience into narrative. Stories contain heroes and villains, struggles, and transformations. They entertain, they teach, they inspire. But why are stories so essential? Some suggest storytelling evolved as a way to pass knowledge safely across generations, embedding lessons in memorable form. Others believe stories bind communities together, giving people shared meaning, identity, and values. Another idea is that storytelling allows us to rehearse life, to explore danger, loss, and hope within the safety set of imagination. Each explanation offers part of the truth, but none fully explain why humans are so deeply drawn to narrative. Stories do more than inform. They move us. They help us make sense of the world and of ourselves, and why the human mind seems wired to turn experience into story remains one more unanswered question quietly woven into who we are. But stories seem to go far beyond any practical role. They create entire worlds that never existed, make us feel deep emotion for people who are not real, and linger in our minds for years, sometimes for a lifetime. No other species does this. Humans return to stories again and again, not just for information, but for meaning. Why the human mind craves narrative so deeply is still unknown. What we do know is that storytelling is as old as language itself, a thread running through every culture, quietly connecting humanity across time. Nature, too, tells stories that science has not yet fully learned to read. Lightning, for example, is usually a brief flash across the sky followed by thunder. But there exists a far stranger phenomenon that has puzzled observers for centuries: ball lightning. Instead of a jagged bolt, witnesses describe glowing spheres of light drifting silently through the air. These orbs, often compared in size to a grapefruit, glow white, orange, or blue, sometimes lasting several seconds before fading or bursting with a soft sound. For a long time, ball lightning was dismissed as myth or illusion. But credible modern sightings and a small number of scientific recordings suggest it is real. The problem is that no one knows what it truly is. Some theories describe plasma trapped by electromagnetic fields. Others suggest vaporized silicon burning slowly after a lightning strike. Still others point to complex chemical reactions in the air. None of these explanations account for all reports. Ball lightning has been seen indoors, drifting through windows without breaking glass, behaving like both light and matter. It appears briefly, unpredictably, and then vanishes, leaving behind questions rather than answers. A ghostly fire passing through history without explanation. Another mysterious glow appears during moments of upheaval beneath our feet. During certain powerful earthquakes, witnesses have reported strange lights in the sky. These earthquake lights take many forms, flickering blue flames along the ground, lightning like flashes above cities, or luminous orbs hovering near fault lines. Accounts of these lights stretch back centuries, but modern cameras have now confirmed that they do occur. What causes earthquake lights remains uncertain. One theory suggests that immense stress within rocks releases electrical charges that ignite the surrounding air. Another proposes that tectonic forces ionize gases near the surface, causing them to glow. But not all earthquakes produce lights, and their appearance varies widely. In some cases, the lights appear before the shaking begins, raising the idea that they could serve as a warning signal. Yet their rarity and unpredictability make them difficult to study. Earthquake lights remain among the most eerie natural phenomena, flashes of otherworldly glow during moments of destruction, hints that Earth itself still hides secrets written in energy and stone. Volcanoes offer another reminder of how little we truly understand. Most volcanic eruptions are dramatic but limited. Lava flows, ash clouds, and small explosions shape landscapes and disrupt lives, but remain within expectations. And then rarely a volcano erupts with overwhelming force. Entire mountains explode. Ash rises into the stratosphere. Sunlight dims. Climate shifts. Crops fail across continents. These super eruptions are among the most powerful events on Earth, yet the triggers behind them are not fully understood. Scientists monitor pressure gas buildup, magma movement, and seismic activity. They can identify warning signs, but predicting exactly when a volcano will cross the threshold from manageable eruption to global catastrophe remains beyond our reach. The Earth's interior is vast, complex, and only partially visible to us. Volcanoes remind us that beneath the solid ground, we trust in immense forces are always moving, waiting, building toward moments we cannot yet foresee. What turns a quiet volcano into a global catastrophe remains uncertain. Scientists understand that pressure builds as magma rises and gases expand, but the precise moment when a system crosses from stability into violent eruption is still difficult to predict. Some volcanoes sleep silently for centuries before erupting without warning. Others release steam, ash, and tremors for years, yet never explode. The mystery lies in what finally tips the balance. History records eruptions of almost unimaginable scale. Krakatoa in 1883 shattered an island and sent shockwaves around the planet. Tambora in 1815 darkened skies worldwide, leading to the year without a summer. The eruption of Mount Toba roughly 74,000 years ago may have been so powerful that it pushed early human populations to the brink of extinction. These events released energy comparable to vast arsenals of modern weapons. And yet, despite advanced instruments and constant monitoring, science still cannot reliably predict when or where such super eruptions will occur. Volcanoes remind us that Earth itself is alive, driven by forces that still elude full understanding. Equally debated is why plate tectonics began on Earth at all. Our planet's surface is in constant motion. Continents drift, mountains rise, oceans open and close, all powered by tectonic plates sliding slowly over the mantle below. Without this movement, Earth would lack many of its defining features. Earthquakes, volcanoes, mountain ranges, and perhaps even life itself depend on this restless activity. But why does Earth have plate tectonics, while nearby planets do not? Mars and Venus show little to no sign of active plate movement. Their crusts appear largely stagnant. Somewhere early in Earth's history, the planet's outer shell fractured into massive plates that began to move. How this happened remains unclear. Some scientists suggest water played a key role weakening rocks and allowing them to bend and slide. Others point to Earth's internal heat, balanced just enough to allow flow without locking the crust in place. Another idea proposes that massive ancient impacts cracked the surface, setting plate motion in motion. Computer models explore these possibilities, but none fully explain why Earth alone developed long lasting plate tectonics. Without it, the carbon cycle that stabilizes climate might not function, and Earth could have become a barren world. Plate tectonics makes our planet dynamic and habitable, yet its origin remains one of the great unsolved puzzles of planetary science. The mystery deepens when we consider Earth's water. Water covers most of the planet, filling oceans, shaping weather, and sustaining every known form of life. Yet its origin is still debated. One possibility is that water arrived from space, delivered by asteroids and comets during the chaotic early days of the solar system. Many of these objects contain ice, supporting this idea. But chemical studies show that the isotopic signature of Earth's water does not always match that found in comets, complicating the picture. Another theory suggests that much of Earth's water was present from the beginning, locked deep within minerals in the mantle. Over billions of years, volcanic activity could have slowly released this water to the surface, forming oceans and atmosphere. There may be truth in both ideas, with water arriving from space while also rising from within. Still, the full story remains incomplete. How Earth acquired and retained such vast quantities of water while neighboring planets became dry or hostile is one more question without a final answer. Together, volcanoes, drifting continents, and endless oceans reveal a planet shaped by hidden processes operating over immense spans of time. Earth feels familiar beneath our feet, yet its deepest workings remain mysterious. And as we trace these unanswered questions, we are reminded that even our home world still holds secrets waiting quietly beneath the surface. Perhaps both ideas are true. Some of Earth's water may have formed here, while some arrived from space. The balance between these sources is still debated. What is clear is that Earth is unusual. Nearby planets, such as Venus and Mars, are largely dry. Their water was either lost to space or locked away beneath the surface. Somehow, Earth gathered vast oceans and kept them stable for billions of years. Water feels ordinary because it is everywhere in our lives, yet its presence is extraordinary. Every sip you take carries a history that reaches back to the formation of the planet itself a quiet mystery flowing through every drop. The moon presents another puzzle. For most of human history, we saw only one face of it. The far side remained hidden until spacecraft revealed it in the 20th century. What they found was unexpected, the near side. The face familiar to us is marked by dark Maria wide plains of ancient lava. The far side looks completely different. It is rugged, heavily cratered, and almost entirely lacking those dark, volcanic seas. Why should two sides of the same moon be so different? Several ideas have been proposed. One suggests that Earth's gravity caused uneven heating long ago, keeping one side warmer and more volcanically active. Another points to a massive ancient impact that reshaped one hemisphere more than the other. Some theories focus on internal differences, variations in crust, thickness, or heat flow that allowed lava to reach the surface on one side, but not the other. Yet none of these explanations fully solve the puzzle. The moon should be more symmetrical than it is. Even now, with orbiters and landers exploring its surface, the far side remains partly unknown, as if the moon still keeps one face turned away from us. Deep beneath the Earth's surface lies another hidden mystery. More than 3,000 kilometers below our feet, Earth's core churns in darkness. A molten outer layer of iron and nickel surrounds a solid inner core, and its motion generates the magnetic field that protects our planet. This invisible shield deflects harmful solar wind and cosmic radiation. Without it, Earth might resemble Mars stripped of atmosphere and life. Yet, despite its importance, we do not fully understand how the core works. We cannot reach it directly. Instead, scientists rely on indirect evidence, seismic waves from earthquakes patterns locked into ancient rocks and complex computer models. We know the outer core flows like a liquid and that this movement drives the geodynamo. But why the magnetic field sometimes weakens drifts or changes direction remains uncertain. Mars once had a magnetic field, but lost it. Why Earth maintained its shield while Mars did not is still an open question. The heart of our planet continues to beat unseen, its influence felt, but its workings largely hidden. From time to time, Earth's magnetic poles reverse. North becomes south, and south becomes north. These reversals are recorded in layers of rock, forming a striped history of flips stretching back millions of years. The most recent full reversal occurred about 780,000 years ago. Why these reversals happen is not fully understood. Scientists believe turbulence in the liquid outer core can destabilize the magnetic field, causing it to weaken and then rebuild in the opposite orientation. But what triggers this instability remains unclear. Some reversals happen relatively quickly, others unfold over thousands of years. Sometimes the field weakens significantly without fully flipping at all. This raises further questions. During these periods, Earth is exposed to higher levels of radiation. Did such events affect ecosystems or influence evolution in the past? We do not yet know. What we do know is that Earth's magnetic field is not permanent. One day the poles will change again, and the reason why remains hidden deep within the planet. Climate too follows cycles we do not fully understand. Over millions of years, Earth has shifted repeatedly between ice ages and warmer periods. Vast ice sheets advanced across continents and then retreated, reshaping landscapes and life itself. These changes are recorded in ice cores, sediments, and fossils. We know that subtle shifts in Earth's orbit, variations in tilt, and changes in sunlight play a role, but these factors alone do not explain the full rhythm of ice ages. Feedback loops involving oceans, atmosphere, ice, and life itself complicate the picture. Small changes can amplify into global transformations. Why these cycles occur with the timing and intensity they do remains uncertain. Ice ages remind us that Earth's climate is dynamic, capable of dramatic change, even without human influence. Our planet breathes on timescales far longer than a human life, and the forces behind those breaths are still only partly understood. Vast glaciers have repeatedly advanced and retreated, carving valleys, reshaping continents, and rewriting the surface of the planet. Why this cycle occurs remains debated. Some explanations focus on subtle changes in Earth's orbit and axial tilt, known as Milankovitch cycles, which alter how sunlight is distributed across the globe. Others point to massive volcanic eruptions, shifting ocean currents, or feedback loops involving carbon dioxide and ice. It may be that all of these forces work together in complex ways we do not yet fully understand. What is certain is that these cycles of ice and thaw have shaped the course of human history. Early humans migrated in response to changing climates, adapting to harsh cold and seizing opportunities during warmer periods. Ecosystems shifted, species evolved, and civilizations flourished when conditions allowed. Yet the deeper engine driving these recurring ice ages remains elusive. They remind us that Earth's climate is not static, but part of a vast and dynamic system whose full workings remain hidden. At times, change comes not gradually, but with sudden violence. Throughout Earth's history, mass extinctions have struck with devastating force. At least 5 times, life has nearly vanished. The extinction that ended the age of dinosaurs 66 million years ago is the most familiar, linked clearly to an asteroid impact. But even larger catastrophes came before it. The Great Dying around 250 million years ago erased most life on Earth in a relatively short span of geological time. Asteroid impacts, colossal volcanic eruptions, dramatic climate shifts, and changes in ocean chemistry have all been proposed as causes. In some cases, evidence points to a single dominant event. In others, multiple disasters may have overlapped, creating cascading failures across ecosystems. Why some species vanish while others survive remains just as mysterious. Why mammals endured when dinosaurs did not. Why some extinctions unfold slowly while others strike almost instantly. Mass extinctions reveal both the fragility and resilience of life. Each catastrophe cleared space for new forms to emerge, reshaping the tree of life. Yet the forces behind these events remain only partly understood. Beyond Earth mysteries continue across the solar system. Saturn's rings are among the most striking sights, known vast bands of ice and dust encircling a giant planet. They stretch hundreds of thousands of kilometers yet are astonishingly thin, sometimes only tens of meters deep. For centuries, scientists assumed they were as old as Saturn itself, formed more than 4 billion years ago. But recent evidence challenges this idea. The rings appear unusually clean, composed mostly of bright ice, with very little dark dust. If they were ancient, countless micrometeorite impacts should have darkened them over time. Data from the Cassini spacecraft suggests the rings may be only a few 100 million years old, extremely young by cosmic standards. If so, how did they form so recently? One possibility is that a moon strayed too close and was torn apart by Saturn's gravity. Another suggests that comets or asteroids shattered spreading debris into orbit. Yet none of these explanations is confirmed. The mystery deepens when we consider that Saturn's rings may be temporary. They are slowly falling into the planet and may disappear within the next 100 million years. If so, we are living during a brief window in cosmic time when Saturn wears this luminous crown. The origin of the rings remains one of the solar system's most beautiful unanswered questions. Uranus presents a puzzle just as strange. Unlike the other planets, Uranus spins almost entirely on its side. Its axis is tilted by 98 degrees, causing it to roll through space rather than spin upright. As it orbits the sun, one pole can face continuous sunlight for decades, while the opposite pole remains in darkness. The seasons on Uranus are extreme and unlike anything on Earth. Why Uranus is tilted so dramatically remains unknown. One leading idea suggests a massive collision early in the planet's history knocked it onto its side. Another proposes that a series of smaller impacts gradually tipped it over. Some models suggest complex gravitational interactions with other bodies during the formation of the solar system. Yet no explanation fully accounts for all observations, including the unusual behavior of Uranus's moons and magnetic field. Uranus rolls silently through the outer solar system, carrying the scars of an ancient event we cannot directly observe. Its sideways spin is a reminder that even familiar planets can hold deep and unresolved mysteries written into their motion across the dark. How Uranus came to roll through space on its side remains an open question. The leading idea suggests that long ago, a colossal collision with a protoplanet struck Uranus with enough force to knock it over. Yet such an impact should have left clearer evidence, perhaps an unusually large moon or lasting scars in the planet's structure. Another possibility is that a series of smaller impacts gradually tipped the planet over time. Some scientists also propose that powerful gravitational interactions with other giant planets during the early chaos of the solar system slowly pulled Uranus into its unusual orientation. Whatever the cause, Uranus remains unique. Its extreme tilt produces strange seasons and may also explain why its magnetic field is oddly tilted and offset from its center. No spacecraft has visited Uranus since Voyager 2 passed by in the 1980s. Until we return, The planet continues its silent sideways journey, carrying a mystery written into its spin. Venus presents an equally puzzling history, often called Earth's twin because of its similar size and mass. Venus could not be more different. One of its strangest traits is its rotation. While most planets spin in the same direction as their orbit, Venus turns the opposite way. On its surface, the sun rises in the west and sets in the east. Even more strangely, a single day on Venus lasts longer than a full year. How this came to be remains debated. One idea suggests a massive impact early in Venus's history reversed its rotation. Another proposes that tidal forces between Venus and the Sun gradually slowed and flipped its spin. A third theory suggests that Venus once rotated rapidly, like Earth, but interactions between its dense atmosphere and surface slowly altered its rotation over time. None of these explanations fully accounts for all observations. Beneath its thick clouds of carbon dioxide and sulfuric acid, Venus turns slowly backward, guarding a history we have yet to fully uncover. Farther out, Neptune reveals a world of violent motion we do not yet understand. At the edge of the solar system, Neptune's winds roar at speeds exceeding anything found on Earth, reaching nearly 2,000 kilometers per hour. Massive storms rise and fade across its deep blue atmosphere, often without warning. The most famous of these, the Great Dark Spot, was discovered by Voyager 2 in 1989. It was a storm roughly the size of Earth itself. Yet when astronomers looked again years later, it had vanished completely. Since then, new dark spots have appeared shifted and disappeared, defying prediction. Neptune receives very little energy from the distant sun, so why its weather is so extreme remains unclear. Some scientists believe internal heat rising from deep within the planet powers these storms. Others think complex atmospheric dynamics amplify small disturbances into enormous tempests. Neptune remains a distant storm wrapped world visited by only one spacecraft, reminding us how little we know about the outer reaches of our own solar system. Jupiter holds one of the longest lived storms ever observed. The Great Red Spot has been swirling for centuries, visible through telescopes for more than 350 years and possibly much longer. It is a colossal storm large enough to engulf Earth, rotating counterclockwise in Jupiter's southern hemisphere. Why it formed and how it has persisted for so long remain unanswered questions. Jupiter's atmosphere is a turbulent ocean of gas with powerful jet streams and deep convection. The Great Red Spot may be sustained by energy drawn from these surrounding flows, but recent observations show it is slowly shrinking. Whether the storm will fade away or continue for centuries more is unknown. Its uncertain future reminds us that even the most enduring features of the solar system are not permanent. Across the planets, strange rotations, violent storms, and ancient scars tell stories we cannot fully read. Each world carries clues from the chaotic birth of the solar system frozen into motion and atmosphere. As we look outward, planet by planet, we are reminded that even familiar names hide unfamiliar histories. The solar system is not a finished story, but a collection of ongoing mysteries quietly unfolding in the dark. Fueled by Jupiter's immense atmosphere, the Great Red Spot has long seemed almost timeless. And yet, careful measurements over recent decades reveal a quiet change. The storm is shrinking. Once vast enough to swallow three Earths side by side, it now spans little more than one. Scientists debate what this means. Why did such a storm form in that particular latitude? How has it survived for centuries when storms on Earth dissolve in days? And is its slow fading the beginning of an end, or simply part of a long cycle we have yet to understand? The Great Red Spot stands as a contradiction in motion, ancient yet delicate, a reminder that even the giants of the solar system are not immune to change. Far beyond the planets, comets emerge from a realm we have never seen. For thousands of years, humans have watched these glowing visitors streak across the sky, their luminous tails pointing away from the sun. We now believe they come from an enormous, distant reservoir known as the Oort cloud. This cloud may contain trillions of icy bodies, remnants left behind from the solar system's formation. It stretches so far that its outer edge may blend into interstellar space itself. And yet, despite its vastness, the Oort cloud has never been observed directly. Its objects are too small, too distant, too faint. We know it exists only through the comets. It sends inward silent messengers, hinting at an unseen population beyond Pluto. How exactly this cloud formed, how far it extends, and whether it is influenced by passing stars remain unanswered questions. The Oort cloud is a hidden shell surrounding our solar system, an invisible frontier filled with ancient ice and unanswered mysteries. Closer in many moons, conceal oceans beneath frozen surfaces, and what lies within them remains unknown. Beyond Earth, liquid water appears in unexpected places. Moons such as Europa, Enceladus, and Titan hide vast oceans beneath thick layers of ice. Some of these oceans may contain more water than all of Earth's seas combined. They remain liquid because of tidal heating, the constant stretching and squeezing caused by the gravity of the planets they orbit. What makes these hidden oceans so compelling is their potential to host life on Earth. Wherever water persists, life follows. In the deep oceans of our own planet, hydrothermal vents support thriving ecosystems that do not depend on sunlight. Could similar environments exist beneath the alien ice? We already see intriguing clues. Enceladus ejects towering plumes of water vapor and ice particles into space rich with organic molecules. Europa's fractured surface suggests a restless ocean beneath, possibly interacting with the rocky seafloor below. Titan, with its complex chemistry, may host environments unlike anything on Earth. Yet we cannot see into these oceans directly. Are they home only to simple microbes, or could they support more complex forms of life, shaped by entirely different conditions? Until probes dive beneath the ice or sample these waters directly, the answers remain sealed away in darkness. Enceladus, in particular, continues to astonish. Its icy surface cracks open, releasing jets of water that escape into space, forming a glowing plume visible from afar. Something below is warm, active, and dynamic, but what drives this activity and what kind of environment it sustains beneath the ice remains uncertain. Beneath that frozen shell may lie one of the most promising habitats beyond Earth, quietly existing in the cold shadows of the outer solar system. What stirs below remains unknown, waiting for a future moment when we finally look beneath the ice and listen to what the ocean has to say. Saturn's small moon, Enceladus, appears quiet at first glance, just a smooth, bright sphere of ice drifting through the cold outer solar system. But when NASA's Cassini spacecraft flew past, it revealed something astonishing. From deep fractures near the South Pole, towering geysers erupted into space, spraying water vapor and fine ice grains hundreds of kilometers above the surface. Within those plumes, scientists detected salts, organic molecules, and chemical signatures that on Earth would point toward environments capable of supporting life. Beneath Enceladus's frozen crust lies a global ocean kept warm by the immense tidal forces of Saturn's gravity. The moon flexes as it orbits, generating heat deep inside. The geysers may be cracks where this hidden ocean vents directly into space, offering us rare samples from an alien sea. What powers these eruptions is still unclear. Some researchers believe hydrothermal vents may exist on the ocean floor, similar to those in Earth's deep oceans, where life thrives without sunlight. Others suggest different unknown processes may be at work. Enceladus is small, only about 500 kilometers across, yet it has become one of the most promising places to search for life beyond Earth. Until new missions return, what truly stirs beneath its ice remains an open question. Titan Saturn's largest moon presents a mystery of a very different kind. It is a world that feels strangely familiar and utterly alien at the same time. Titan has rivers, lakes, and seas shaped by rain and erosion, but none of them contain water. Instead, liquid methane and ethane flow across its surface beneath a thick, hazy atmosphere. Clouds gather, storms form, and methane rain falls, carving channels much like those on Earth. The puzzle lies in persistence. Methane in Titan's atmosphere should be broken apart by sunlight over geological time. If nothing replaced it, Titan's seas should have vanished long ago, yet they remain. Something must be replenishing the methane. Some scientists suspect cryovolcanoes, icy volcanoes, that release methane from deep within the moon. Others point to chemical reactions in Titan's interior that we do not yet understand. A more provocative idea suggests biology. Methane can be a potential sign of life, though not definitive. Titan's methane cycle eerily mirrors Earth's water cycle, but the source that keeps it running remains hidden, quietly sustaining this alien world. Mars tells another story, one written in dry riverbeds and silent valleys. Billions of years ago, Mars was not the frozen desert we see today. Its surface was shaped by flowing rivers, long-lasting lakes, and perhaps even vast oceans. Deltas spread out, where water once slowed and channels snake across the landscape, unmistakable signs of a wetter past. Today, Mars is cold and dry, its atmosphere thin and fragile. Where did all the water go? Some may be locked away as ice beneath the surface. Some may be trapped inside minerals. Much of it may have escaped into space after Mars lost its magnetic field, leaving the planet exposed to the solar wind. But the full story remains incomplete. Did Mars dry out gradually, or did it undergo sudden catastrophic changes? Could liquid water still exist underground, hidden from our instruments? Understanding the fate of Martian water may be key to knowing whether life once existed there and whether it might still persist in secret. As we search the skies and distant worlds, another mystery follows us everywhere. Mathematics describes the universe with astonishing precision, yet we do not know why. Mathematics is a system of symbols and rules created by human minds, and yet it maps onto reality with uncanny accuracy. Equations written on paper govern the motion of planets, the behavior of light, and the structure of its atoms. Einstein's equations predicted black holes decades before they were observed. Maxwell's formulas described electromagnetic waves long before radios existed. Why should abstract mathematics align so perfectly with the physical universe? Some believe mathematics is not invented, but discovered, revealing structures already woven into reality. Others argue that the human mind evolved to recognize patterns, and mathematics is simply the best tool we have developed to describe them. But neither explanation fully resolves the mystery. Why should the same equations describe the arc of a thrown stone and the motion of distant galaxies? Why does the universe seem to speak fluently in the language of numbers? This quiet harmony between mind mathematics and cosmos remains one of the deepest and most unsettling mysteries of all. Mathematics stands at a strange crossroads. It is created by the human mind, yet it unlocks the workings of the universe with astonishing precision. Equations imagined on paper govern stars, atoms, and the flow of time itself. Why this abstract language fits reality so perfectly remains one of existence's deepest mysteries. Beneath every physical law lie numbers that never change. The speed of light, the mass of an electron, the strength of gravity. These constants set the rules of the cosmos. Alter them even slightly, and stars might never ignite. Chemistry might collapse, and life as we know it could never arise. We can measure these values with incredible accuracy, but we cannot explain why they are what they are. Some scientists argue they are simply cosmic accidents. Others imagine a vast multiverse where countless universes exist with different settings, and we inhabit the rare one that allows observers to emerge. For now, these ideas remain beyond proof. The constants of nature feel like precise dials set long ago, defining reality without explanation, a quiet background melody we can hear but never trace to its composer. Even randomness itself is uncertain. On the surface, chance seems obvious. Coins flip unpredictably. Dice roll without pattern. But physics complicates this simple picture. At the quantum level, particles behave in ways that appear fundamentally unpredictable. An electron does not follow a single path. A radioactive atom decays without warning. There is no hidden clock we can point to. Is this true randomness, or only a sign that deeper laws remain hidden from us? Einstein famously rejected the idea, insisting that the universe could not be governed by chance. He believed unseen rules must guide every event. Yet decades of experiments suggest that quantum uncertainty may be real, not just ignorance. Some physicists now think randomness is woven into reality itself, not as a flaw, but as a feature. If that is true, then uncertainty is not merely what we do not know, it is part of what the universe is. Whether reality is ultimately ordered or fundamentally random remains one of physics' most profound unanswered questions. Time itself deepens the mystery. We live immersed in time, feeling it carry us from moment to moment. And yet science struggles to define what time actually is. Einstein revealed that time is flexible. It slows near massive objects and speeds up at higher altitudes. It stretches and compresses depending on motion and gravity. Space and time are fused into a single fabric, shaping the universe together. But our experience of time feels one directional. The past is fixed, the future remains open. Memories flow backward, never forward. Some physicists link this arrow of time to entropy, the gradual increase of disorder. But that explanation only shifts the puzzle. Why did the universe begin in such an ordered state that entropy could even increase? Others suggest time itself may be an illusion emerging from deeper processes beyond our perception. Time governs every breath and heartbeat, yet its true nature remains elusive, one of the deepest riddles science has yet to solve. Matter itself carries a similar mystery. When the universe was born, theory predicts that matter and antimatter should have formed in equal amounts. When the two meet, they annihilate into pure energy. If they had been perfectly balanced, everything should have vanished almost instantly. No galaxies, no stars, no life. And yet something tipped the scales. Matter survived. Experiments show that matter and antimatter behave nearly the same, but not quite. Tiny asymmetries exist, subtle differences that may have allowed matter to gain a slight advantage in the earliest moments of the cosmos. That small imbalance was enough to build everything we see today. But why it exists remains unknown. The universe chose matter over antimatter by the smallest margin imaginable, and that choice made existence possible. Why reality favored one over the other is still one of the most haunting questions in cosmology. These tiny asymmetries may have nudged the early universe in one direction rather than another, but they still feel insufficient to explain the full outcome. Somewhere hidden in the earliest moments of cosmic history lies the reason why existence survived at all. Until that reason is uncovered, the triumph of matter over antimatter remains an unanswered riddle, a quiet imbalance that allowed everything else to follow. Mass itself carries a similar mystery. Everything we touch, every star we see, every cell in our bodies has weight and substance. Yet for much of modern physics, no one knew where mass came from. The discovery of the Higgs boson confirmed that an invisible field fills all of space. As particles move through this field, They gain resistance, and that resistance appears to us as mass. Without it, atoms could not form stars, could not shine, and matter would pass through itself like ghosts. And yet, this explanation only reaches so far. Why does the Higgs field exist at all? Why does it have the precise strength that it does? Why do some particles interact with it strongly, while others barely notice it? The Higgs answered one question, but revealed deeper ones beneath it. Mass feels solid and fundamental, but its origin remains partly hidden in unseen fields that quietly shape reality. Even the structure of reality itself is uncertain. To human senses, the universe feels smooth and continuous. Space seems endlessly divisible, like a line that can be split forever. But at the deepest levels, this may not be true. Some theories suggest reality is granular, built from indivisible units like pixels on a screen. If so, space and time themselves would have a smallest possible scale, beyond which the idea of smaller loses meaning. This hypothetical limit is known as the Planck scale, unimaginably tiny, far smaller than anything we can measure. At that scale, space may no longer be smooth, but foamy and unstable, fluctuating with quantum uncertainty. If reality is truly pixelated, the laws of physics would need to be rewritten from the ground up. Yet so far, no experiment has confirmed this picture. Whether the universe is continuous or discretized remains one of the strangest open questions in science. Physics has always pushed inward. Atoms were once thought indivisible until they were split into smaller parts. Protons themselves turned out to be built from quarks. But there may come a point where division stops a final layer beneath which nothing smaller exists. If such a limit is real, then reality has a bottom floor, a smallest brick from which everything else is built. Whether that floor exists remains unknown. The laws themselves deepen the mystery. Gravity, electromagnetism, quantum mechanics. These rules govern everything from falling apples to distant galaxies. They are elegant and consistent, but they are not inevitable. They could have been different. A universe with slightly altered laws might never form stars, or might collapse too quickly, or drift apart into emptiness. Why do our laws permit complexity, structure, and life? Some physicists imagine countless universes, each running on its own set of rules. In that view, ours is not special, only compatible with observers. Others believe there must be deeper principles that lock the laws into place, principles we have not yet discovered. For now, we can describe how the rules work, but not why these rules exist instead of others. And perhaps this leads to the most profound question of all. Will we ever fully understand any of this? Science has carried us remarkably far. We have charted the evolution of galaxies, uncovered the structure of atoms, decoded the language of genes, and stepped onto another world. Yet with every answer comes a widening horizon of new questions. Each discovery reveals deeper layers of mystery. The universe does not seem built to be fully revealed all at once. It invites curiosity, rewards patience, and then retreats just beyond reach. Perhaps understanding is not a destination, but a journey, one that unfolds slowly, generation by generation. As we search, the questions themselves continue to shape us, reminding us that we are explorers within a reality far larger and more subtle than we can yet comprehend. And for now, as these questions drift quietly through your mind, you can let them fade into the background. The universe does not demand answers tonight. It simply continues vast and mysterious while you rest within it. Perhaps one day we will uncover the origins of consciousness, the first spark of life, the beginning of the universe, and the true nature of time itself. Or perhaps some questions will always remain just beyond our reach, not because we have failed to understand them, but because they are woven into the fabric of existence itself. It may be that the greatest mystery is not the universe, but our place within it. Whether a human mind shaped by evolution and limited by perception can ever fully grasp the totality of reality. As you slowly drift towards sleep, you can hold that thought gently without needing to resolve it. Curiosity itself may be part of the answer. To wonder is to be human. To question is to be alive. Tonight you have journeyed through 100 of science's greatest mysteries. Questions that stretch from the smallest processes inside your own cells to the farthest edges of the cosmos. Each one is a reminder that no matter how much we have learned, reality remains deeper, stranger, and more beautiful than we can fully comprehend. Think for a moment about what we've touched together. The quiet emergence of consciousness, the fragile riddles of memory and aging, the hidden oceans beneath frozen moons, the restless storms of distant planets, the unseen laws that shape space-time and matter itself. Some of these mysteries may be solved within your lifetime. Others may take centuries, and some may never yield answers at all. But that is not a failure. It is part of the wonder. To live in a universe filled with unanswered questions is to live in a universe full of possibility. Every mystery is an open door. Every unknown is an invitation. The fact that we do not yet know keeps science alive, keeps curiosity burning, and keeps us leaning gently forward into the future. Now, as you rest here, allow these mysteries to drift softly through your mind. Notice how they no longer demand effort or answers. Like waves moving slowly across a quiet shore, the questions themselves can be calming. They don't need to be solved tonight. They only need to pass through you like starlight moving across a dark sky. Let your breathing settle into a slow, natural rhythm. Let your body grow heavy, supported by the surface beneath you. Let your thoughts soften and loosen their grip. Imagine yourself floating gently through the vast landscape of mysteries we've explored. Questions above you, questions below you, a galaxy of wonder surrounding you on all sides. And there at the quiet center of it all is you, safe, resting, at ease, knowing that mystery is not something to fear, but something to embrace. If you're still awake later, you can always continue exploring when you're ready. But for now, there is nothing left to do. No answers to chase, no puzzles to solve, only the calm certainty that mystery itself can be a kind of lullaby, carrying you gently into sleep. Good night, and may your dreams be filled with wonder.